There's something haunting about the silence of space, a vast, endless void where our most advanced machines orbit Earth, unseen and unheard. These satellites, the unsung heroes of modern life, keep our world connected. They guide us home, predict storms before they strike, and beam the internet to every corner of the globe. But what happens when they fail? Picture this. One moment, your GPS locks onto your destination, and the next it's gone. Weather forecasts vanish, leaving coastal towns blind to approaching hurricanes. Global communications stutter, then collapse. This isn't the plot of a dystopian movie. It's happened before, and it will happen again. Satellite failures aren't just technical glitches, they're stark reminders of how fragile our grasp on the universe truly is. Every time a satellite goes dark, it's like a crack in the foundation of our confidence. We build these marvels of engineering, launch them into the unknown, and trust them to work flawlessly for years. But space doesn't play by our rules. Solar flares erupt without warning, radiation fries delicate circuits, and even the tiniest design flaw can unravel a mission worth billions. Each failure forces us to confront an uncomfortable truth. For all our knowledge, we're still at the mercy of forces we barely understand. Take the case of a famous weather satellite that suddenly spun out of control, its cameras pointing uselessly into the void. Or the navigation satellite that began broadcasting errors, throwing off everything from airplane routes to financial transactions. These aren't just malfunctions, they're cosmic wake-up calls. So what do these breakdowns teach us? They reveal the limits of human ingenuity, but also its resilience. Every failure is a lesson etched in metal and code, pushing scientists and engineers to dig deeper, innovate harder, and respect the universe's unpredictability. In this video, we'll uncover the stories behind these celestial mishaps, the engineering oversights, the cosmic surprises, and the moments when humanity had to admit it didn't have all the answers. Because sometimes it's the things that go wrong that teach us the most about how to move forward. Stick around, because what you're about to discover might just change how you see the sky and our place in it forever. The story of Sputnik is a humbling one, a tiny beeping sphere no bigger than a beach ball, yet it sent shockwaves across the world. When it launched in 1957, it wasn't just a technological triumph, it was proof that humanity could reach beyond Earth. But that triumph came with a sobering lesson. After just 3 weeks, Sputnik's batteries gave out, and its iconic beeps fell silent. Imagine the disappointment of those early engineers, watching their creation go dark so soon after making history. This wasn't just a minor hiccup, it was the first real glimpse of how unforgiving space could be. What made Sputnik's failure so revealing was how it exposed the gaps in our thinking. Back then, engineers were so focused on the sheer challenge of getting a satellite into orbit that they hadn't fully considered how to keep it running. There were no backup systems, no fail-safes, just a single set of batteries that, once drained, left the satellite useless. In hindsight, it seems obvious, but at the time, it was a wake-up call. If something as monumental as Sputnik could falter so quickly, what did that mean for the future of space exploration? Yet Sputnik's legacy isn't just about its short life, it's about how that failure reshaped the way we approach space technology. Engineers began designing systems with redundancy, building in extra power sources and backup components to keep satellites operational even if one part failed. They started thinking in terms of years, not weeks, planning for the long haul rather than just the launch. And perhaps most importantly, they learned to embrace setbacks as part of the process. Every satellite that followed, from weather monitors to deep space probes, carried echoes of Sputnik's lesson. Progress isn't just about reaching new heights, it's about staying there. What's striking is how Sputnik's story mirrors the broader human experience. We celebrate our breakthroughs, but it's often the stumbles that teach us the most. That first silent satellite didn't just mark the start of the space age. It showed us that even our greatest achievements are fragile, and that humility is just as vital as ambition when reaching for the stars. Sometimes the smallest errors carry the heaviest consequences. Take Mariner 1, a spacecraft designed to make history by flying past Venus, until a single missing hyphen in its guidance code sent it spiraling off course. Just 4 minutes after launch in 1962, ground controllers had no choice but to trigger the self-destruct mechanism. A mission costing millions vanished in flames, all because one symbol was left out of thousands of lines of code. What makes this failure so unsettling is how ordinary it was. There were no solar storms, no cosmic mysteries, just a human mistake. The software was supposed to correct the rocket's path automatically, but without that critical hyphen, it misinterpreted sensor data, steering wildly off course. Engineers later called it the most expensive hyphen in history, but the real cost wasn't just financial. The setback delayed planetary exploration by months, forcing teams to rebuild and retest everything from scratch. Yet Mariner 1's story isn't just about a typo. It's about the illusions we shatter when things go wrong. We imagine space missions as flawless triumphs of precision, but they're built by people. People who get tired, who overlook details, who trust systems a little too much. The mission's post-mortem revealed something profound. The error slipped through because multiple safeguards had failed. A rushed schedule, overconfident reviews, even the way the code was handwritten on paper before being transferred to punch cards, each layer had a weak spot. What emerged from the ashes was a new era of humility in spaceflight. NASA overhauled its procedures, implementing stricter checks and redundancies for every line of code. But the deeper lesson lingered. No matter how advanced our technology becomes, human judgment remains both its greatest strength and its Achilles heel. Mariner 1 didn't fail because space was hostile. It failed because we hadn't yet learned to respect our own limitations. That missing hyphen became a symbol of something far bigger, a reminder that in the race to conquer the cosmos, the greatest obstacles might not lie in the stars, but in the quiet, easy-to-miss corners of our own minds. Every mission since carries that lesson forward, written not just in code, but in the culture of those who dare to reach beyond Earth. The Hubble Space Telescope was supposed to give us the clearest view of the cosmos ever seen, a window to the universe with unprecedented clarity. But when its first images came back in 1990, scientists were horrified. Instead of crisp, dazzling stars, they saw blurry smudges. The problem: a flaw in Hubble's primary mirror so slight you could barely measure it, just 1/50th the width of a human hair. Yet that microscopic error was enough to scatter light, turning what should have been groundbreaking discoveries into frustrating puzzles. What made this failure so shocking was the sheer irony of it. Here was a telescope representing the pinnacle of human engineering, a project decades in the making, undone by something as simple as a miscalculation. The mirror had been ground with near-perfect precision, but near-perfect isn't good enough when you're capturing light from billions of light years away. The error traced back to a testing device that had been assembled incorrectly, a tiny misalignment no one noticed until it was too late. Suddenly, the world's most advanced space telescope was, in the words of one astronomer, a $2.5 billion nearsighted telescope. But Hubble's story doesn't end with that mistake. What happened next was nothing short of extraordinary. scientists and engineers refused to give up. They designed a set of corrective optics, essentially a pair of cosmic glasses, to counteract the mirror's flaw. Installing them required one of the most complex spacewalks in history, with astronauts working in zero gravity to fit the delicate components with surgical precision. When the first corrected images came through, the difference was breathtaking. Distant galaxies snapped into focus, nebulae revealed intricate structures, and Hubble finally delivered on its promise. This wasn't just a technical fix, it was a testament to human ingenuity. Hubble taught us that perfection isn't the absence of flaws, it's the willingness to confront them. The telescope went on to revolutionize astronomy, uncovering black holes, measuring the expansion of the universe, and capturing iconic images like the pillars of creation. None of that would have happened if we'd let that initial failure define the mission. Hubble's legacy isn't just about the science it enabled, it's about the mindset it embodied. Space exploration isn't a straight line from failure to success. It's a cycle of stumbling, learning, and pushing forward. That flawed mirror became a symbol of something profound. Our greatest achievements aren't the ones that go perfectly, but the ones where we refuse to let imperfection stop us. Every stunning image Hubble sent back was a reminder that sometimes the most important discoveries begin with a mistake. Galaxy 15 wasn't supposed to become a ghost. This communications satellite, orbiting silently above Earth, had one job: relaying signals across continents. But in 2010, something went terribly wrong. A powerful solar storm scrambled its systems, and just like that, Galaxy 15 stopped responding to commands. Yet, unlike other failed satellites that drift silently into oblivion, this one refused to die. Its transmitters kept blasting signals at full power, creating chaos in the crowded orbital highways above us. What made Galaxy 15 so unnerving was how it behaved like something out of a sci-fi nightmare. It wasn't just dead, it was undead, a zombie satellite haunting the very networks it was meant to serve. As it drifted uncontrolled, its rogue transmissions began interfering with other satellites, disrupting television broadcasts, emergency communications, even air traffic control signals. Engineers on the ground scrambled to reroute traffic, but Galaxy 15 wouldn't be ignored. It became a stark example of how fragile our orbital infrastructure really is. One malfunctioning machine could send ripples of disruption across the globe. The real horror wasn't the satellite's defiance, but our helplessness to stop it. Normally, a rogue satellite could be commanded to shut down or move to a safer orbit. But Galaxy 15's brain was fried, locked in a state where it couldn't hear instructions, yet its body kept functioning on autopilot. For months, engineers watched helplessly as it lumbered through space, threatening to collide with other satellites or amplify its interference as it drifted into new orbital slots. It was a chilling reminder that once we launch something into space, we don't always get to decide when its mission ends. Yet Galaxy 15's story isn't just a cautionary tale, it's a mirror held up to our own ambitions. We fill the skies with machines, assuming we can control them indefinitely. But space doesn't work that way. Radiation, micrometeoroids, even the unpredictable fury of the sun can turn our most advanced technology into wandering hazards. What saved us in the end wasn't some dramatic intervention, but something far simpler: time. Galaxy 15's batteries eventually drained, and the zombie finally fell silent. But the question it left behind still echoes: how many more of these ghosts are we creating up there? And when will one come back to haunt us in ways we can't fix? The legacy of Galaxy 15 lingers in every new satellite design, every redundancy added to prevent another runaway machine. It taught us that space isn't just a frontier to conquer, it's a wilderness where our creations can slip their leash. And in that vast, silent expanse, the line between tool and threat is thinner than we'd like to admit. Imagine a weather satellite designed to be our eyes in the sky, constantly scanning for wildfires, tracking hurricanes, and monitoring atmospheric changes that could save countless lives. That was GOES 17, one of the most advanced weather satellites ever built. But in 2018, something went terribly wrong. Its infrared sensors, crucial for detecting heat signatures from fires and storms, began failing. The reason, a cooling system meant to protect its delicate instruments had quietly stopped working. What started as a minor blockage in a tiny loop of tubing spiraled into a full-blown crisis, leaving meteorologists scrambling to fill the gaps in their forecast. The irony was brutal. Here was a billion-dollar machine packed with cutting-edge technology, brought to its knees by something as mundane as a clogged pipe. Engineers later discovered that debris had accumulated in the coolant loop, likely leftover material from manufacturing or assembly. It was the kind of oversight that might go unnoticed in a car's air conditioning, but in space, there's no easy fix. Without proper cooling, the satellite's infrared cameras overheated, rendering them useless during the hottest parts of the day. Suddenly, a tool designed to warn us of disasters was blind when we needed it most. What made this failure so unsettling was how it exposed the fragility of our assumptions. We build these satellites to withstand solar radiation, micrometeoroid impacts, and the vacuum of space, yet something as simple as a speck of debris can cripple them. GOES 17's designers had accounted for extreme temperatures, but not for the coolant system failing from the inside out. It was a reminder that sometimes the biggest threats aren't cosmic forces, but the tiny, overlooked flaws in our own craftsmanship. Yet the story doesn't end with the failure. Engineers refused to give up. They devised a workaround, reprogramming the satellite to operate its infrared sensors only during cooler orbital periods. It wasn't a perfect solution, but it salvaged about 80% of the instrument's capabilities. That ingenuity speaks to a deeper truth about space technology. Failure isn't always final. Sometimes it's an invitation to innovate under pressure. The legacy of GOES 17 isn't just a cautionary tale, it's a blueprint for resilience. Future satellites now undergo even stricter cleaning protocols, with coolant systems tested under conditions meant to mimic decades in orbit. But perhaps the most valuable lesson lies in the humility it forced upon us. No matter how advanced our machines become, they're still human creations, vulnerable to human oversights. And in the silent, unforgiving expanse of space, even the smallest oversight can echo louder than we ever imagined. The story of OCO2 reads like a cosmic thriller, a mission balancing on the edge of disaster before it even began. In 2009, NASA Orbiting Carbon Observatory was poised to become our most sophisticated tool for tracking carbon dioxide, the invisible gas driving Earth's climate crisis. But as the countdown reached zero and the rocket roared skyward, something went catastrophically wrong. The protective fairing, the shell meant to shield the satellite during launch, failed to separate. Trapped under that extra weight, the spacecraft never stood a chance. It plummeted back to Earth, vanishing into the ocean near Antarctica just 17 minutes after liftoff. A decade of meticulous planning, and all that remained was debris sinking into icy waters. What made this failure so devastating wasn't just the loss of hardware. OCO2 wasn't just another satellite, it was designed to answer existential questions. How much CO2 are oceans absorbing? Which regions are emitting more than they should? Without this data, we're essentially flying blind in the fight against climate change. The accident exposed a chilling truth. Our ability to monitor the planet's health hinges on machines that can vanish in an instant. One malfunctioning latch, one misaligned seal, and suddenly humanity loses its eyes on a critical piece of the climate puzzle. Yet what happened next reveals the resilience threaded through space exploration. Scientists refused to let that failure be the end. They scavenged spare parts, redesigned vulnerable systems, and rebuilt the satellite from the ground up. 5 years later, OCO2 finally made it to orbit, this time flawlessly. Today, it circles Earth every 99 minutes, its spectrometers dissecting sunlight to measure carbon dioxide with pinpoint accuracy. Each pass adds another layer to our understanding, revealing how forests, cities, and even ocean currents shape the atmosphere's composition. But the ghost of that first failure lingers. OCO2's near miss reminds us how thin the margin for error really is. Had NASA not secured funding for a rebuild, we'd be missing millions of data points crucial for climate models. Cities wouldn't know their true emissions. Scientists wouldn't see how droughts or wildfires alter the carbon cycle. It's a stark lesson. In space, as in climate science, there are no second chances unless we fight for them. The satellite's second act proves something profound. Sometimes the most important journeys aren't the ones that go smoothly, but the ones we have to restart from scratch. Every time OCO2 detects a spike in CO2 over a rainforest or tracks the seasonal pulse of plant growth, it's not just collecting data, it's whispering a reminder. The tools we rely on to understand our changing world are as fragile as the planet they observe. And that's why every launch, every satellite, every byte of data matters more than we realize. Space doesn't just sit quietly, it rages. While we picture it as a silent, empty expanse, the reality is far more violent. Solar flares erupt without warning, hurling waves of charged particles across millions of miles. Cosmic radiation, invisible and relentless, pierces through even the most hardened satellites like a ghostly knife. These aren't rare events. They're the background noise of the universe, a constant reminder that our fragile machines orbit in a shooting gallery. Take the Halloween solar storms of 2003, a cosmic tantrum that turned our skies into a light show while quietly wreaking havoc above us. Satellites flickered like candles in a breeze. GPS signals wobbled, throwing off navigation systems by hundreds of feet. Airlines rerouted flights to avoid radiation exposure, and some spacecraft went into emergency shutdowns to survive the particle bombardment. All this chaos came from a single cluster of sunspots, a blemish on the sun's surface no bigger than Earth itself. What makes space weather so terrifying is its unpredictability. Unlike hurricanes or earthquakes, we can't see these storms coming until they're almost upon us. A solar flare takes just 8 minutes to reach Earth, barely enough time for operators to brace for impact. And the damage isn't always immediate. Radiation can linger, gnawing at satellite components like termites in wood, until one day a critical system just stops. Yet the real lesson here isn't just about the danger, it's about the illusion of control. We build satellites to withstand the vacuum of space, the extremes of heat and cold, but the universe always finds new ways to surprise us. Engineers now armor their spacecraft with shielding, design redundant systems, even program satellites to temporarily play dead during solar storms. But these are just band-aids on a wound that never fully heals. The irony is poetic. We launch these marvels of technology to study the cosmos, only to be humbled by the very forces we're trying to understand. Each solar storm, each burst of radiation whispers the same truth. Space doesn't care about our plans. It's a reminder that for all our ingenuity, we're still guests in a realm where the rules are written by something far greater than ourselves. And sometimes, the most important thing a satellite can teach us isn't about the stars, it's about learning to survive in their shadow. Kessler syndrome sounds like science fiction, a slow-motion disaster where space becomes so cluttered with debris that collisions trigger more collisions until Earth is wrapped in a swirling shell of shrapnel. But this isn't a plot twist from a blockbuster movie. It's a real and looming threat, one that could trap us on our own planet. The idea, first proposed by NASA scientist Donald Kessler in 1978, reads like a cautionary fable. One collision creates hundreds of fragments, each capable of destroying another satellite, creating thousands more fragments in a nightmarish domino effect. And the scariest part, we've already had front-row seats to how easily this could unfold. Take the 2009 collision between an active Iridium communications satellite and a defunct Russian Cosmos satellite. Traveling at nearly 26,000 miles per hour, the impact wasn't just a fender bender. It was an explosion, scattering over 2,000 large fragments across orbit. Each piece became a bullet capable of piercing through other satellites or even the International Space Station. Suddenly, mission controllers were tracking a cloud of debris, calculating evasion maneuvers to protect their billion-dollar assets. This wasn't just an accident, it was a warning shot. The math behind Kessler syndrome is brutally simple. Space might seem infinite, but the orbits we rely on for GPS, weather monitoring, even internet access are surprisingly cramped. Add in the fact that debris can stay in orbit for centuries, and you've got a recipe for disaster. Right now, we're tracking over 30,000 pieces of space junk larger than a softball, and millions more too small to detect. A single collision like Iridium Cosmos could double that number overnight, pushing us closer to the tipping point where cleanup becomes impossible. What makes this scenario so chilling isn't just the loss of satellites, it's the paralysis that would follow. Imagine a world where launching new satellites is too risky, where the debris field is so dense that rockets can't safely pass through it. No more Hubble replacements to peer deeper into the cosmos. No more Mars rovers or lunar landers. Even the International Space Station would become a sitting duck, its crew forced to evacuate. We'd be locked out of space, watching from the ground as our own trash circled endlessly above us. Yet there's a glimmer of hope in this grim forecast. The same ingenuity that got us into this mess might yet get us out. Scientists are testing nets, harpoons, and even lasers to capture or nudge debris out of orbit. Companies are designing satellites that can deorbit themselves at the end of their lives, burning up harmlessly in the atmosphere, and international agreements are slowly pushing for stricter rules on space traffic management. But time isn't on our side. Every new satellite launched, every piece of debris left unchecked, brings us one step closer to Kessler's nightmare. The lesson here isn't just about engineering or orbital mechanics, it's about responsibility. Space isn't a dumping ground, it's a shared frontier, one we've only begun to explore. The choices we make now, how we design, launch, and retire our satellites will echo for generations. Kessler syndrome isn't just a theory, it's a mirror reflecting back the consequences of our carelessness. And if we don't like what we see, there's still time to change it before the sky above us becomes a prison of our own making. Military satellites operate in a world of shadows and silence, where failures are rarely acknowledged but carry consequences far beyond their classified missions. Take the case of Zuma, a mysterious payload launched in 2018 atop a Falcon 9 rocket. Officially, SpaceX declared the launch a success. The rocket performed flawlessly. But Zuma never made contact. Some reports suggest it failed to separate from the upper stage, plunging back into the atmosphere. Others whisper it reached orbit only to go dark immediately. The truth remains locked away, but the implications are stark. When a billion-dollar military asset vanishes without explanation, It's not just a technical hiccup, it's a geopolitical tremor. What makes these failures so unnerving is the secrecy surrounding them. Civilian satellites like Hubble or GOES-17 have public postmortems, with engineers sharing lessons learned. But military satellites, their very purpose relies on stealth and ambiguity. A malfunctioning spy satellite might mean missed warnings of missile launches, gaps in surveillance over conflict zones, or the sudden loss of secure communications for troops in the field. During the Cold War, a single faulty early warning satellite nearly triggered nuclear war when it mistook sunlight glinting off clouds for incoming missiles. Only a sharp-eyed officer's skepticism prevented catastrophe. The stakes are even higher today. Modern militaries depend on satellites for everything from drone strikes to encrypted battlefield coordination. Imagine a scenario where a nation's reconnaissance satellites blink out during a crisis, leaving leaders to make decisions blind. Suspicion takes over. Was it a solar storm? A cyber attack, an act of sabotage. History shows how easily misunderstandings escalate when visibility vanishes. And unlike commercial satellites, there's no backup network to fill the gap. These systems are often one of a kind, their capabilities known only to a handful of cleared personnel. Yet perhaps the most chilling aspect is how these failures ripple beyond military circles. A navigation satellite glitch might delay a supply convoy, but a military ComSat failure could derail ceasefire talks or mask the movements of armed factions. Even environmental monitoring has a hidden martial edge. When a weather satellite dies, it's not just forecasts that suffer. Missile trajectories, drone operation ranges, and naval routes all rely on atmospheric data. The line between civilian and military space infrastructure is thinner than we'd like to admit. What emerges from these shadows isn't just a tale of technology, but of trust or the lack thereof. Every unreported malfunction fuels paranoia. Every orbital gap invites speculation. And in a world where satellites are both shields and swords, their failures don't just risk lives, they risk stability itself. The next time a classified satellite goes dark, we may never know, but the silence will speak volumes. The race to blanket Earth with internet satellites feels like something out of a sci-fi novel. Thousands of machines, each no bigger than a coffee table, working in unison to beam the web to every corner of the globe. Companies like SpaceX and OneWeb promise to bridge the digital divide, connecting remote villages and underserved cities with speeds rivaling fiber optics. But behind this utopian vision lies a quieter, messier reality. For every successful launch, there's a satellite that never wakes up, a solar panel that refuses to unfold, or a thruster that sputters and dies. The Iridium Next constellation, a network of 66 satellites meant to revolutionize global communications, saw at least 10 units fail within years of launch. Some drifted silently out of position, others simply stopped responding. These weren't isolated glitches, they were symptoms of a broader tension tearing through the industry. The push to scale quickly versus the need to build things that last. What makes this dilemma so urgent is the sheer pace of deployment. SpaceX alone has permission to launch nearly 12,000 Starlink satellites, with plans for tens of thousands more. Each new batch rolls off assembly lines at breakneck speed, designed to be cheap, disposable, and rapidly replaceable. On paper, it's a brilliant strategy. If one satellite fails, another can take its place. But space isn't a factory floor. Dead satellites don't just vanish, they linger, cluttering orbits and increasing the risk of collisions. And while companies tout redundancy as a safety net, there's a darker side to this approach. When failure becomes expected, corners get cut. The result, satellites with shorter lifespans, less rigorous testing, and components chosen for cost over resilience. The irony is hard to miss. These constellations are built to connect us, yet their very design might be setting us up for a disconnected future. Take the case of a single Starlink satellite that malfunctioned in 2021, not by drifting silently, but by actively steering itself into the path of other satellites. Ground controllers had to scramble to avoid a chain reaction of near misses. It was a stark reminder that even small, mass-produced satellites can become hazards when they misbehave. And with tens of thousands planned, the odds of more going rogue only increase. But the debate isn't just about engineering, it's about ethics. When companies prioritize shareholder timelines over satellite longevity, who bears the risk? Farmers relying on internet for precision agriculture, sailors navigating by satellite-linked charts, or hospitals in war zones depending on telemedicine. These aren't just customers. They're people whose lives could hinge on a signal that suddenly drops because a cost-cutting decision years earlier chose cheaper solar cells. The promise of universal connectivity shouldn't come at the cost of reliability, yet the financial incentives often point in the opposite direction. There's a glimmer of hope in the chaos. Some companies are pushing back against the throwaway model, investing in satellites with longer lifespans and easier repairability. Others are exploring in orbit, servicing essentially tow trucks for space that could extend missions or rescue failing satellites before they become debris. But these solutions move slower than the launch schedules, racing against an industry barreling toward an orbital traffic jam. The question we're left with isn't just about technology, it's about time. How long until the trade-offs catch up with us? When does fast and cheap become broken and dangerous? The answers might not come from boardrooms or launch pads, but from the silent, empty spots in the sky where another satellite was supposed to be. We think of satellites as untouchable, orbiting far beyond reach, shielded by the vastness of space. But in 2008, Landsat 7, a NASA Earth observation satellite, proved just how wrong that assumption was. For 12 minutes, hackers seized control, not through some high-tech space weapon, but with a laptop. They didn't steal data or crash the system. They simply demonstrated it could be done. That breach was a wake-up call, a flashing red light revealing how exposed our orbital infrastructure really is. The terrifying part isn't just that satellites can be hacked, it's how easy it is. Many still rely on outdated software, unencrypted signals, or ground systems with gaping security holes. In 2019, researchers showed how they could hijack a communications satellite by intercepting its unsecured uplink, essentially tricking it into accepting malicious commands. Imagine the chaos if someone rerouted a GPS satellite, shifting navigation coordinates by just a few hundred feet. Planes could veer off course, shipping lanes would become hazard zones, and military operations could spiral into disaster. This isn't hypothetical. Cyber attacks on satellites are already tools of modern warfare. During Russia's invasion of Ukraine, hackers targeted Viasat's satellite internet network, crippling communications for thousands. The attack didn't just disrupt battlefield coordination, it knocked out wind turbines and emergency services across Europe, proving how interconnected and fragile these systems are. And it's not just governments at risk. Private satellites controlling everything from ATMs to irrigation systems are equally vulnerable. A single breach could freeze financial markets or blind farmers to incoming storms. The stakes escalate when you consider how few safeguards exist. Unlike nuclear weapons, there are no treaties governing satellite cybersecurity. A hacker in a basement could theoretically trigger an international crisis by tampering with the wrong satellite. An attribution figuring out who's responsible might take weeks if it's possible at all. Even scarier, some satellites can't be patched once they're in orbit. A flaw discovered after launch might stay there, a ticking time bomb waiting to be exploited. Yet there's a twist in this grim narrative. The same openness that makes satellites vulnerable also fuels innovation. Many space agencies now crowdsource security flaws, inviting ethical hackers to stress test systems before criminals do. Companies are building satellites with self-healing networks that can isolate breaches mid-orbit, and a new wave of quantum encryption promises signals so secure, even the most sophisticated hackers couldn't crack them. The lesson of Landsat 7 isn't that we should fear the future. It's that we have to build it with eyes wide open. Every satellite we launch carries not just instruments and antennas, but the hopes and risks of a world that depends on them. The next time you check the weather on your phone or follow a map to a new destination, remember, there are invisible battles raging above us, and the front line isn't just in space, it's in the code. There's a quiet cemetery orbiting Earth one few people ever talk about. It's not marked by headstones or flowers, but by the lifeless husks of dead satellites, thousands of them, drifting in what engineers call graveyard orbits. These forgotten machines are more than just space junk. They're eerie monuments to our own technological ambition, and they might hold a clue to one of the universe's greatest mysteries, the Fermi paradox. If the cosmos is so vast with billions of potentially habitable planets, why does it feel so empty? Where are all the other civilizations? The answer could be lurking in our own backyard, in the silent graveyard we've built above us. Think about it. Every failed satellite up there represents a moment when our best technology betrayed us. A solar panel that didn't deploy, a computer that froze, a thruster that misfired, small glitches with cosmic consequences. Now imagine scaling that up. What if the same thing happens not just to satellites but to entire civilizations? The physicist Enrico Fermi first posed this chilling question in the 1950s. With so many stars and planets, statistically, intelligent life should be everywhere. Yet we see no signs of interstellar empires, no alien megastructures, not even a single radio signal. It's as if the universe is a stage set for a play where all the actors have vanished before the curtain rises. One explanation, known as the Great Filter, suggests there's some catastrophic hurdle civilizations can't overcome, a point where their own technology outpaces their ability to control it. Nuclear war, runaway climate change, artificial intelligence gone rogue, or maybe something as mundane as space debris. Picture this: a civilization advances enough to fill its orbit with satellites, but not enough to clean them up. Collisions multiply, creating a shrapnel storm that makes spaceflight impossible. Trapped on their home planet, they watch helplessly as their machines turn their sky into a prison. No more telescopes to search the stars, no more probes to explore neighboring worlds, just silence and the slow decay of everything they built. The parallels to our own situation are hard to ignore. Right now, we're adding satellites to orbit faster than ever, tens of thousands planned in the next decade alone, yet we still don't have a reliable way to remove defunct ones. We're playing a high-stakes game of orbital Jenga, stacking pieces higher while praying the tower doesn't collapse. The Kessler syndrome isn't just a theory, it's a countdown clock, and every dead satellite we leave up there ticks us closer to midnight. But here's the twist: what if this isn't just a warning? What if it's a test? The universe might be silently judging which civilizations are wise enough to tame their own inventions. Maybe the reason we haven't found aliens isn't because they never existed, it's because they didn't survive their own version of satellite graveyards. And now the same forces that might have erased them are unfolding right above our heads. This isn't just about space junk, it's about the choices we make as a species. Do we learn from the ghosts in our orbit, or do we join them? The answer could determine whether we're remembered as the civilization that reached for the stars or the one that got tangled in its own nets. Artificial intelligence was supposed to make satellites smarter, more resilient, more independent. Instead, it's given them something eerily human, the capacity to make mistakes. Take the case of E5, a top-secret U.S. military communications satellite that suddenly went rogue in 2019. Designed to operate autonomously for years, its advanced AI began misinterpreting commands from the ground, executing maneuvers that made no logical sense. Engineers watched helplessly as the billion-dollar asset drifted unpredictably, its algorithms trapped in a feedback loop of confusion. What was meant to be a triumph of machine intelligence became a glaring reminder that autonomy comes with risks we're still learning to measure. The irony is hard to miss. We build these systems to handle the unpredictable nature of space solar flares, debris collisions, communication blackouts, only to find that their greatest vulnerability might be their own programming. Modern satellites use AI for everything from avoiding collisions to diagnosing internal failures, but that self-sufficiency comes at a cost. Without human oversight, an AI might solve a problem in ways we never anticipated. Picture a weather satellite that misreads a sensor glitch as a catastrophic failure, shutting down essential instruments during a hurricane, or a deep space probe that interprets cosmic radiation as an alien signal, wasting precious power chasing ghosts. The more responsibility we hand to machines, the more creative their failures become. What makes these glitches so unsettling isn't just the technology, it's the trust we place in it. We're entering an era where satellites don't just follow orders, they make decisions. Some can already reroute their own missions, prioritize data collection, even negotiate with other satellites for bandwidth. On paper, it's efficiency perfected, but history shows how quickly efficiency can spiral into chaos. In 2018, a European Earth observation satellite's AI mistook a routine software update for a cyber attack, triggering a lockdown that took weeks to reverse. Meanwhile, its cameras sat idle, missing critical climate data. The very systems meant to protect these machines can end up paralyzing them. The question isn't whether AI belongs in orbit, it's how much leash we give it. Right now, there are no universal standards for autonomous satellite behavior, no rulebook for when a machine should override human commands. Different countries, different companies, even different satellite models all follow their own logic. That patchwork of protocols is a recipe for disaster. Imagine two satellites from rival nations interpreting the same orbital threat differently, one dodging left while the other veers right, colliding in a cloud of debris. The consequences wouldn't just be technical, they'd be diplomatic, yet for all the risks, pulling back isn't an option. The sheer volume of satellites now in orbit makes human-only control impossible. Ground teams can't micromanage thousands of machines in real time, especially when signals take seconds or even minutes to travel between Earth and spacecraft. AI isn't just convenient, it's becoming essential. The challenge is building safeguards that match our ambition. Some engineers are pioneering explainable AI systems that don't just make decisions, but can articulate why they made them. Others are designing kill switches that force satellites to pause and await human confirmation when facing unfamiliar scenarios. The lesson of E5 isn't that autonomy is flawed, it's that autonomy is young. We're teaching machines to think like us, complete with our capacity for error. Every anomaly, every glitch, every rogue maneuver is part of that education. A reminder that intelligence, artificial or otherwise, isn't infallible. The satellites orbiting above us aren't just tools anymore, they're students, and whether they graduate with honors or flunk out spectacularly might depend on how well we've written the syllabus. There's a quiet truth about satellites that most people never consider. They're all living on borrowed time. Designed to last 5, 10, maybe 15 years, these machines often cling to life decades past their expiration dates, their components aging in the harsh environment of space like explorers stranded in a desert. NASA's timed mission was supposed to last just 2 years, studying Earth's upper atmosphere. Instead, it kept going for 17, outlasting its original team of engineers and becoming a poster child for endurance. Then, in 2021, its systems began failing one by one. First, a glitch in its data recorder, then erratic power fluctuations. Finally, the satellite that had defied expectations for so long fell silent, not with a dramatic explosion, but with a whimper. What makes Timed Story so revealing isn't just its longevity, it's the illusion of permanence it created. We grow accustomed to satellites that outlast their warranties, treating them like immortal sentinels in the sky. But space is a relentless foe. Solar radiation degrades solar panels, cosmic rays fry delicate circuitry, and even the metal skeleton of a satellite slowly weakens under constant temperature swings. The longer a satellite operates beyond its intended lifespan, the more it's held together by luck and ingenuity rather than design. Ground teams become like emergency room doctors, performing triage on aging systems, shutting down non-essential functions, rerouting power, praying the next glitch won't be the one that kills the patient. The stakes are higher than you might think. Take GOES 12, a weather satellite that operated for 13 years, 10 more than planned. When it finally failed in 2013, meteorologists lost a critical eye on hurricanes forming over the Atlantic. Backup satellites scrambled to fill the gap, but for weeks, forecasters worked with blurrier data, like a pilot suddenly flying through fog. The same scenario plays out across industries. Navigation satellites drifting out of position cause GPS errors that ripple through shipping lanes and financial markets. Aging communications satellites sputter, dropping signals mid-call or mid-transaction. These aren't hypotheticals, they're the inevitable cost of an orbital infrastructure built on machines running on fumes. Yet there's a paradox at the heart of this longevity. Engineers don't deliberately design satellites to fail. They build them to survive worst-case scenarios. Over-engineering is standard practice. Extra shielding, redundant systems, components tested far beyond expected stresses. That's why so many satellites last far longer than their official lifespans. But this safety margin creates a dangerous complacency. Budgets tighten when missions end, teams move on to new projects, and the satellite becomes an afterthought until it isn't. By the time problems arise, the experts who built it may have retired, their knowledge lost to time. The lesson here isn't just about engineering, it's about philosophy. We treat satellites like appliances, expecting them to work indefinitely until they don't. But space doesn't forgive neglect. Every extra year a satellite operates is a gift, not a guarantee. The real challenge isn't just building machines that last. It's building systems that gracefully fail when their time comes, without taking critical services down with them. Because in the end, even the hardiest satellite is just one solar flare, one computer crash, one tiny short circuit away from becoming another ghost in the graveyard orbit. And the clock is always ticking. When a satellite fails, it's not just the loss of metal and circuitry, it's the collapse of a financial house of cards. Take that $424 million National Reconnaissance Office launch in 2011, a mission that never made it past the launch pad due to a faulty upper stage. In an instant, years of research, engineering, and taxpayer funding vanished into smoke and debris. But the true cost goes far beyond the price tag of the satellite itself. Factor in the ripple effects, delayed scientific missions, scrambled defense strategies, even insurance premiums that skyrocket for future launches, and suddenly that number feels almost conservative. The economics of space are brutally unforgiving. Unlike a failed car prototype or a cancelled software project, there are no second chances with satellites. Once they're gone, and the losses aren't just measured in dollars. Consider the GOES G-weather satellite, lost in 1986 when its Delta rocket veered off course just 71 seconds after liftoff. Beyond the $75 million spacecraft, its destruction created a gap in hurricane tracking that left coastal communities vulnerable for years. Or the Amos 6 communications satellite, valued at $200 million, which exploded during a routine pre-launch test in 2016, taking with it Facebook's plans to bring internet access to remote parts of Africa. These aren't just budget line items, they're broken promises with real human consequences. What makes these failures so financially devastating is the domino effect they trigger. A single satellite often supports entire industries. Think GPS guiding shipping containers worth billions, or weather data protecting agricultural harvests. When one goes dark, the economic tremors spread far beyond space agencies. After the Galaxy 15 zombie satellite incident in 2010, companies spent millions compensating customers for interrupted TV and radio services. Banks rerouted transactions to avoid timing errors caused by GPS glitches. Airlines burned extra fuel flying longer routes to maintain safety margins. The true cost of failure isn't just what we lose in orbit, it's what we pay to compensate for that loss back on Earth. Yet perhaps the most overlooked expense is opportunity cost. Every dollar spent replacing a failed satellite is a dollar not spent pushing boundaries. The Mars Climate Orbiter, lost in 1999 due to a metric imperial unit mix-up, represented more than $125 million that couldn't fund future Red Planet missions. The Cluster Satellite Quartet, destroyed in a 1996 Ariane rocket explosion, set back magnetospheric research by years until a rebuilt fleet could launch. These aren't just financial setbacks, they're stolen time. Moments when humanity's reach into the cosmos was abruptly shortened. Insurance tells its own grim story. Premiums for satellite launches hover around 10% of total project costs when insurers are willing to cover them at all. After a string of high-profile failures in the 2010s, some providers simply stopped covering certain rocket models. The math is chilling. With launch failures averaging 1 in 20, the industry walks a constant tightrope between affordability and catastrophe. And as satellites grow more complex, packed with cutting-edge instruments that push technological limits, the risks and prices only climb higher. The bitter irony: many failures stem from attempts to save money. The push for cheaper, faster production leads to skipped tests. Pressure to meet quarterly targets overrides caution. Even the choice between established but expensive components versus newer, unproven alternatives becomes a gamble with millions at stake. The Space Shuttle program learned this brutally after the Challenger disaster, when investigations revealed cost-cutting pressures contributed to the fatal O-ring failure. Today's commercial space race faces the same dilemma: how to balance innovation's breakneck pace with the sobering reality that in space, failure doesn't just hurt profits, it rewrites futures. What emerges from these financial ruins isn't just a ledger of loss, but a roadmap for resilience. Every burned million teaches a lesson. Redundancy isn't wasteful, it's essential. Testing isn't a delay, it's an investment. And sometimes the most expensive decision is the one that cuts corners. The next time you check a satellite-powered weather app or follow a GPS route, remember behind that convenience lies an economic tightrope, one that balances on the edge of the void. The Mars Climate Orbiter should have been a triumph, a meticulous machine designed to study Martian weather patterns from orbit. Instead, it became one of the most infamous cautionary tales in space history. In 1999, after a flawless 9-month journey, the spacecraft approached Mars exactly as planned, then vanished without a trace. The culprit? A single staggering oversight. One engineering team used metric units while another worked in imperial. That tiny disconnect caused the orbiter to descend too close to the planet's atmosphere, where it either burned up or ricocheted into space. A $327 million mission reduced to cosmic dust by a conversion error. This wasn't just a case of bad luck, it was a perfect storm of human fallibility. Lockheed Martin's team calculated thruster forces in pounds, while NASA navigation software expected newtons. Nobody caught the mismatch, not during years of development, not in pre-launch checks, not even as the orbiter began its fatal descent. The mistake was almost comically simple, yet its consequences were absolute, and it reveals an uncomfortable truth. No matter how advanced our technology becomes, it's still built and operated by humans, creatures hardwired to overlook the obvious, to trust familiar patterns, to assume someone else has double-checked the math. But human error is only part of the equation. Space itself is a minefield of unpredictable hazards. Solar storms can scramble electronics without warning. Micrometeoroids, some no larger than a grain of sand, punch through shielding at speeds faster than bullets. Even the gentle pressure of sunlight can gradually push satellites off course over decades. The GOES 12 weather satellite survived 13 years in orbit, only to be crippled by a single faulty circuit no bigger than a fingernail. These aren't mistakes we can fix with better training or checklists. They're the universe reminding us how small we really are. The question isn't whether failures will happen, it's how we respond when they do. After the Mars orbiter disaster, NASA overhauled its review processes, mandating that every unit of measurement be verified by independent teams. Modern satellites now carry redundant systems, so if one computer fails, another can take over. Engineers design components to withstand radiation levels far beyond expected exposure, like building a car that can survive a meteor strike. But these solutions come with trade-offs. More redundancy means heavier satellites, which cost more to launch. Excessive shielding adds complexity, creating new points of potential failure. We're stuck in a cosmic catch-22. The harder we try to eliminate risk, the more we create. Perhaps the real lesson lies in embracing imperfection. The Hubble Space Telescope launched with a flawed mirror, yet became legendary after repairs. The Kepler Planet Hunter lost critical gyroscopes, but engineers reinvented it as K2, using sunlight pressure to stabilize its gaze. These stories suggest that failure isn't the end, it's a pivot point. The satellites that truly endure aren't the ones that never break. They're the ones whose designers anticipated the breaking and built a way forward. So can we ever eliminate risk? Probably not, but that's not the goal. Space will always be bigger, stranger, and more hostile than our best preparations. The victories worth celebrating aren't the flawless missions, they're the ones where we stare into the void, admit we don't have all the answers, and keep exploring anyway. Because every failure, every near miss, every brush with cosmic chaos teaches us something new, and in the grand experiment of spaceflight, that's what progress really looks like. Deep space probes carry our boldest dreams into the cosmos, machines built to answer questions no human could reach. Yet for every triumphant mission like Voyager or Curiosity, there are heartbreaks like Mars Observer and Beagle 2, silent reminders of how brutally space tests our ambitions. Mars Observer vanished in 1993, just days before reaching the red planet, its signal cutting off without explanation. Theories swirled: a fuel tank explosion, a computer crash, but the truth remains locked in space's cold vault. Then there's Beagle 2, the UK's plucky Mars lander that made it to the surface in 2003 only to never phone home. Years later, photos revealed it had landed intact. Its solar panels failed to fully deploy, suffocating the mission before it could begin. These failures sting because they're so close to success. Mars Observer carried instruments that could have rewritten our understanding of Martian climate and geology. Beagle 2's tiny lab might have detected signs of life. Instead, they became case studies in cosmic humility. Yet their legacies aren't just about loss, they're about the painful, necessary process of iteration. After Mars Observer's disappearance, NASA redesigned communication systems for future orbiters, adding multiple ways to diagnose and recover from glitches. Beagle 2's solar panel flaw led to rigorous new deployment tests for subsequent landers, ensuring no mission would choke on its own design. What's striking is how these failures expose the gap between our confidence and reality. We send probes across millions of miles, assuming our simulations account for every variable, but space laughs at assumptions. The Soviet Mars 3 lander touched down safely in 1971, then died within 2 minutes, likely felled by a dust storm no model predicted. Even NASA's Genesis probe, designed to capture pristine solar wind particles, crashed into Utah desert in 2004 when its parachutes failed, a flaw traced to sensors installed upside down during assembly. These aren't just engineering oversights, they're glimpses into how chaos thrives in the void. Yet there's an unexpected beauty in these stumbles. Every failed probe leaves behind a trail of hard-won knowledge, like breadcrumbs for the next mission. The Europeans didn't abandon Mars after Beagle 2. They built ExoMars with redundant systems and smarter landing tech. NASA Mars Reconnaissance Orbiter, launched after Observer's loss, became one of the most prolific eyes in the sky precisely because it learned from that silence. Failure isn't the opposite of exploration, it's the price of admission. The deeper lesson here isn't about engineering, it's about mindset. Societies that mythologize exploration often forget how messy it really is. Columbus didn't find a new route on his first try. Early aviators crashed more often than they flew. Space probes are no different. Each lost mission forces us to confront an uncomfortable truth. We're still beginners in this cosmic ocean, fumbling with tools we barely understand. But beginners who keep trying eventually become masters. The next time a probe vanishes into the void, remember, its silence isn't an ending. It's the first whisper of the next breakthrough. Satellite sabotage sounds like something from a spy thriller. Cloaked spacecraft sneaking up on rivals, invisible beams frying electronics from thousands of miles away. But the reality is far murkier, existing in the shadows between speculation and classified operations. Take that infamous 2007 Chinese anti-satellite missile test, where a ground-launched weapon obliterated an aging weather satellite at 500 miles above Earth. The strike wasn't just a show of force, it created a swirling cloud of over 3,000 trackable debris fragments, some still zipping around Earth today at speeds that could puncture the International Space Station. Suddenly, what seemed like science fiction became a chilling precedent. Nations could weaponize orbit itself, turning the very infrastructure we rely on into a battlefield. The line between accident and sabotage grows thinner in the void. In 2022, an unexplained anomaly knocked out thousands of Viasat internet terminals across Europe just as Russia invaded Ukraine. Was it a targeted cyber attack, a coincidental solar flare? The truth remains buried beneath layers of geopolitical posturing. Even subtler tactics exist, like satellite spoofing, where false GPS signals trick navigation systems into drifting off course. Ships have reported suddenly finding themselves miles from their actual positions, their instruments hijacked by invisible hands. These incidents rarely make headlines, but they sketch a disturbing pattern. Space is no longer a sanctuary. It's a chessboard where moves are made in silence, and the collateral damage could be every satellite we depend on. What makes these threats so insidious is their deniability. Unlike a missile launch, cyber intrusions leave no smoke trails. A satellite's sudden malfunction could be space weather or a carefully timed hack. The U.S. has accused Russia of deploying inspector satellites that sidle up to other nations' spacecraft, their intentions opaque. Are they merely observing or testing the waters for something more destructive? The ambiguity itself becomes a weapon, sowing distrust in an environment where trust is the only thing preventing chaos. Yet for all the paranoia, the greatest danger might be the unintended consequences. That Chinese anti-satellite test didn't just anger diplomats, it endangered every spacecraft in low Earth orbit for decades. A single reckless act could trigger Kessler syndrome, turning vital orbital highways into minefield. The irony is crushing. In trying to dominate space, we risk making it unusable for everyone. The lesson here isn't just about military posturing, it's about the fragility of the rules we've barely established. There's no cosmic police force, no intergalactic treaty with real teeth, just a handful of aging agreements and the hope that nations will act responsibly. But as satellites grow more essential and more vulnerable, that hope feels increasingly like a prayer whispered into the void. The next time your GPS glitches or a live feed cuts out, ask yourself, was that a technical hiccup or the opening move in a game no one admits they're playing? Space is the ultimate gambler's arena where even the most meticulously designed satellites can become cosmic lottery winners or cautionary tales based on twists of fate. Take Voyager 1, launched in 1977 with an expected lifespan of 5 years. 46 years later, it's still transmitting data from interstellar space, its systems chugging along through sheer dumb luck, surviving radiation levels and temperatures that should have fried its circuits decades ago. Then there's Hitomi, Japan's cutting-edge X-ray observatory, which spun itself to pieces in just over a month during 2016 because of a software glitch and a rushed response from ground control. One machine dodges every bullet, another falls to a single misstep. The difference between triumph and disaster, sometimes just the universe's mood that day. What makes these contrasts so unsettling is how they expose the illusion of control. Engineers can simulate every conceivable scenario: radiation baths, thermal extremes, micrometeoroid impacts, but space always invents new ways to surprise us. The Hubble Space Telescope's flawed mirror was a manufacturing error we could fix. But what about the cosmic rays that randomly flip bits in a satellite's brain, triggering unpredictable behavior? Or the way solar panels on NASA's Opportunity rover stayed dust-free for years thanks to Martian wind gusts, a stroke of luck that extended its mission 12 times longer than planned. We plan for the probable, but it's the improbable that often writes the story. The randomness isn't just about hardware, it's about timing. A satellite launched during a solar minimum might cruise through its mission unscathed, while one deployed during heightened solar activity faces a gauntlet of radiation storms. The same design, the same team, wildly different outcomes. Consider the twin Mars rovers Spirit and Opportunity, built identically, yet Spirit succumbed to a sand trap after 6 years while Opportunity roamed for 14. The difference wasn't engineering, it was which patch of Martian terrain they happened to roll over. Yet luck isn't purely cosmic, it's also about human moments. The Galileo probe survived a malfunctioning main antenna because an engineer had the foresight to include a backup low-gain system, a decision initially labeled as paranoid overkill. Conversely, the Phobos Grunt Mars mission failed in 2011 when its computer rebooted mid-orbit due to an unanticipated cosmic ray strike, locking itself in a fatal loop. The kicker, a software patch to prevent this exact scenario, existed but hadn't been uploaded before launch. This randomness forces a humbling admission. For all our equations and simulations, space remains a realm where chance plays co-pilot. The satellites that become legends aren't always the best designed. They're the ones that danced through the minefield of the cosmos and lived to tell the tale. And those that fail, they're not necessarily flawed, just unlucky. The lesson isn't to abandon planning, but to respect the chaos, because in the end, every satellite we launch is a message in a bottle tossed into a hurricane. Sometimes it reaches shore, sometimes it doesn't, and that's the gamble of touching the void. Imagine a bullet the size of a paint chip traveling 17,000 miles per hour. That's the reality of space debris. Up there, even a fleck of discarded rocket paint becomes a deadly projectile, capable of punching through satellite armor like tissue paper. The numbers are staggering. Over 128 million fragments of human-made junk now orbit Earth, from spent boosters to shattered satellites, all whipping around the planet at unimaginable speeds. And with every collision, every accidental impact or intentional weapons test, the cloud grows thicker, turning our orbital highways into a demolition derby where the crashes happen silently, violently, and without warning. The story of Hitomi, Japan's state-of-the-art X-ray observatory, serves as a grim case study. In 2016, just weeks after launch, the satellite began spinning uncontrollably. Ground teams fought desperately to regain control, but within hours, Hitomi tore itself apart. While the official cause was blamed on a software glitch, some investigators suspect a debris strike may have triggered the fatal spiral. A piece of metal no bigger than a grain of rice, invisible to tracking systems, could have been the culprit. If true, it's a chilling reminder: in space, even the smallest oversight or the tiniest speck of trash can destroy a mission worth hundreds of millions of dollars. The danger isn't just hypothetical. The International Space Station regularly performs debris avoidance maneuvers, firing thrusters to dodge incoming fragments. In 2021, a Russian anti-satellite test deliberately blew up a defunct satellite, creating a debris field so dense it forced astronauts to shelter in escape capsules. But here's the catch: we can't track everything. Current radar systems monitor roughly 30,000 objects larger than a softball, but millions of smaller pieces, each still capable of catastrophic damage, remain invisible until it's too late. Cleaning up this mess is one of the most urgent and daunting challenges we face. Startups and space agencies are testing wild ideas: nets to snag derelict satellites, harpoons to spear them, even lasers to nudge debris into safer orbits. The European Space Agency's Clear Space mission, slated for 2026, aims to be the first to capture and remove a piece of space junk. But these solutions are like using a thimble to empty an ocean. The real bottleneck isn't technology, it's politics. No international laws mandate debris removal, and the cost of cleanup falls on no single nation. Meanwhile, companies keep launching mega constellations of satellites, adding thousands more objects to an already overcrowded sky. The irony is crushing. We rely on satellites for everything from weather forecasts to banking, yet we're turning their environment into a junkyard. Every piece of debris up there is a legacy of our short-sightedness, a reminder that humanity's greatest talent might be creating problems faster than we can solve them. The clock is ticking. Either we find a way to clean up our cosmic backyard, or we risk trapping ourselves on Earth behind a wall of our own making. And in that scenario, everyone loses. A satellite insurance claim reads like a high-stakes poker game companies wagering millions against the cosmos, hoping their numbers beat the house. Take the case of Arabsat-6 in 2019, a state-of-the-art communications satellite that suffered a crippling power failure just months after launch. The payout, nearly $150 million, one of the largest in industry history. But here's the twist. The satellite had passed every pre-launch test with flying colors. Its failure wasn't due to some dramatic collision or solar storm, just an ordinary electrical short no one saw coming. That's the brutal reality of space insurance. You can model every conceivable risk, but the universe always deals a wild card. The math behind these policies feels almost surreal. Premiums typically run 8 to 12% of a satellite's total value, meaning a $500 million mission might cost $50 million just to insure. And that's if insurers will cover it at all. After a string of high-profile failures in the 2010s, some underwriters simply stopped covering certain rocket models, while others jacked up rates overnight. The reason: space is the ultimate actuarial nightmare. Unlike car crashes or hurricanes, there's no reliable historical data to predict how often satellites will fail. A solar flare might fry one spacecraft while leaving its neighbor untouched. A tiny manufacturing defect could lie dormant for years before triggering catastrophe. Insurers aren't just betting against mechanical failure, they're gambling against chaos itself. What makes these policies so fascinating is what they reveal about our blind spots. When insurers refused to cover early SpaceX Falcon 9 launches until the rocket proved itself, they weren't being paranoid, they were acknowledging how little we truly understand about reusable rocket reliability. Similarly, when Intelsat filed a $225 million claim for Galaxy 19 in 2018 after its solar array stalled, it exposed a vulnerability no one had prioritized: single-point failures in power systems. These aren't just financial transactions, they're stress tests for our entire approach to space engineering. Yet the most revealing claims are the ones that never happen. Many military satellites operate uninsured, their risks deemed too secret or too expensive to underwrite. When a billion-dollar spy satellite fails, taxpayers foot the bill, and the public might never know. It's a stark contrast to commercial operators, where every glitch becomes a line item in an actuarial table. This duality raises uncomfortable questions. If insurers demand rigorous safety standards for civilian satellites, why don't governments hold themselves to the same scrutiny? The answer might lie in the cold calculus of national security, where the cost of failure is measured not in dollars, but in geopolitical advantage. The future of satellite insurance is hurtling toward even murkier territory. With mega constellations like Starlink adding thousands of cheap, mass-produced satellites to orbit, underwriters face a dilemma: how to price policies for machines designed to be disposable. Traditional models assumed each satellite was a precious, irreplaceable asset, but what happens when failure is baked into the business plan? Some insurers are experimenting with parametric policies that pay out based on predefined triggers like a solar storm's intensity, rather than individual satellite failures. Others are leveraging AI to predict cascading risks, like how one collision might spawn debris that threatens dozens of other insured assets. Beneath all the spreadsheets and risk assessments, space insurance is really a mirror. It reflects our growing dependence on orbit and the uncomfortable truth that we're building a house of cards in a hurricane. Every claim, every denied policy, every recalibrated premium whispers the same warning: we're not as in control as we'd like to think. And in the high-stakes casino of space, the house always wins eventually. Behind every satellite failure, there's a team of engineers staring at screens as their years of work unravel in real time. Japan's Akatsuki Venus probe was supposed to be a crowning achievement, a mission to unlock the secrets of Venus's violent atmosphere. In 2010, after a flawless launch, its main engine failed during orbit insertion, sending the probe tumbling past its target into the void. The control room footage from that moment is heartbreaking. Faces frozen in disbelief, hands clutching heads, the slow-motion collapse of a dream. These aren't just technical setbacks, they're emotional earthquakes for the people who pour their lives into these machines. The psychological toll of these failures lingers long after the news cycles fade. Engineers describe sleepless nights replaying every decision, wondering if a different material, an extra test, or a last-minute adjustment might have changed the outcome. For the Akatsuki team, the grief was compounded by an agonizing 5-year limbo as they fought to salvage the mission. Using tiny attitude thrusters never designed for such a maneuver, they slowly nudged the probe back toward Venus, executing a desperate backup plan that finally succeeded in 2015. That triumph couldn't erase the trauma of the initial failure, only repurpose it into something new. What makes these stories so human is the raw vulnerability they expose. We mythologize space exploration as a series of heroic victories, but the reality is messier. The engineers who built NASA's Mars Polar Lander in 1999 didn't just lose a machine when it crashed, they lost a piece of themselves. The investigation revealed the lander's software had mistaken vibrations from deploying its legs for touchdown, shutting off the engines 100 feet above the surface. For the team, that tiny coding oversight became a lifelong shadow, a reminder of how easily brilliance can be undone by a single unnoticed flaw. Yet there's an unspoken resilience in these narratives. The same people who endure these crushing losses are often the first to volunteer for the next mission, to push for riskier experiments, to stare down the void again. ESA's Schiaparelli Mars lander team faced global scrutiny when their probe smashed into the red planet in 2016. Instead of retreating, they published every byte of failure data, turning their heartbreak into a public lesson for future missions. That transparency, that willingness to turn pain into progress, is the quiet courage that fuels exploration. The deeper truth here isn't just about engineering perseverance, it's about the cost of ambition. Every satellite that fails carries the fingerprints of countless individuals who dreamed bigger than their tools allowed. Their grief isn't a sign of weakness, it's proof of how deeply they care. And in an age where space travel is increasingly commercialized, these human stories anchor us to what really matters, not the cold calculus of profit margins, but the burning desire to reach beyond what we know. The next time a satellite vanishes into silence, remember, it's not just metal and code that's lost. It's someone's midnight oil, their missed birthdays, their stubborn hope that this time, against all odds, the universe might just say yes. The graveyard orbit isn't just a resting place for dead satellites, it's a classroom. Among the silent machines drifting thousands of miles above Earth, engineers find some of their most valuable lessons written in metal and malfunction. Take Envisat, the European Space Agency's 8-ton environmental sentinel that went silent in 2012. Designed to monitor everything from ocean currents to atmospheric pollution, its abrupt failure left scientists scrambling. But what seemed like an ending became a beginning. When investigators pieced together the clues, they uncovered a flaw no one had anticipated: thermal stress. For a decade, Envisat had endured brutal temperature swings, 200 degrees Celsius difference between sunlight and shadow. Each pass around Earth flexing its components like a paperclip bent repeatedly. Over time, microscopic cracks formed in its power system, unnoticed until the day they severed a critical connection. This wasn't just bad luck, it was a revelation. Engineers had assumed materials could handle such cycles, but Invisat proved even space-grade alloys have limits. Its failure forced a radical rethink of thermal protection, leading to new alloys and flexible circuit designs that now guard successors like the Sentinel satellites. The beauty of satellite archaeology lies in these unexpected gifts from the void. NASA's Solar Max mission in the 1980s taught a similar lesson the hard way. After its attitude control failed, leaving it spinning uselessly, the agency pulled off the first ever in-orbit repair via space shuttle. But the postmortem revealed something startling. The satellite's fuses had blown not from a cosmic event, but because engineers hadn't accounted for electrical surges during intense solar activity. That oversight became a cornerstone of modern power system design, preventing countless failures since sometimes the lessons are cultural, not technical. When the Hitomi X-ray Observatory disintegrated in 2016, JAXA investigation uncovered a chilling pattern. Engineers had noticed anomalies during testing, but dismissed them under pressure to meet launch deadlines. The result, a $300 million telescope reduced to debris. This tragedy sparked a paradigm shift in Japan's space program, prioritizing open reporting of concerns over rigid schedules, a change that likely saved their next flagship mission, XRISM. What makes these postmortems so powerful is their honesty. Space agencies once shrouded failures in secrecy, fearing reputational damage. Today, missions like ESA's Aeolus wind mapping satellite publish detailed failure analyses online, turning their stumbles into global teaching moments. When Aeolus's laser, a critical instrument, began degrading unexpectedly, teams worldwide studied the data, leading to improved cooling systems for future space lasers. The legacy of dead satellites isn't just in the fixes they inspire, but in the humility they instill. Every failure whispers the same truth: we don't know what we don't know. Engineers now build satellites with lessons learned databases, ensuring Invisat thermal stress or Solar Max's electrical flaws never repeat. But the real breakthrough is philosophical, accepting that each mission, whether it lasts weeks or decades, is part of a longer conversation between humanity and the cosmos. And sometimes the most important data doesn't come from a satellite's instruments, but from its silence. When Cosmos 954 streaked across Canadian skies in January 1978, it wasn't just a satellite burning up, it was a geopolitical grenade detonating on impact. The Soviet reconnaissance satellite, packed with radioactive uranium to power its systems, scattered debris across hundreds of miles of pristine wilderness. Cleanup teams in hazmat suits recovered fragments emitting radiation levels 50 times higher than safe limits, turning a remote corner of the Northwest Territories into an accidental nuclear waste site. What followed wasn't just a technical disaster. It was the first real test of who answers for humanity's orbital recklessness. The legal battle that unfolded set a troubling precedent. Under the 1972 Space Liability Convention, the Soviet Union was technically responsible, but the fine print left gaping loopholes. Moscow eventually paid Canada $3 million in compensation, less than half the cleanup cost after years of tense negotiations. That paltry sum became the price tag for irradiating another nation's territory, revealing how ill-prepared international law was for the era of space debris. Today, with over 5,000 satellites orbiting Earth and thousands more planned, Cosmos 954's legacy feels more urgent than ever. Who pays when a defunct SpaceX satellite collides with a Chinese space station? What happens when a rogue communications satellite jams another country's military frequencies? The answers remain murky, trapped in a tangle of outdated treaties and national interests. The moral questions cut even deeper. unlike oil spills or industrial accidents, space junk transcends borders effortlessly. A single collision can spawn debris that threatens every nation's satellites indiscriminately. Yet there's no global fund for orbital cleanup, no mandatory insurance for commercial operators, not even universal tracking standards for derelict spacecraft. Private companies like OneWeb and Amazon's Project Kuiper are racing to launch mega constellations while shouldering minimal responsibility for the long-term consequences. It's a 21st century tragedy of the commons unfolding in slow motion, where the incentives to pollute orbit far outweigh the rewards for preserving it. Consider the case of the abandoned Envisat, a European satellite the size of a bus that's been drifting uncontrolled since 2012. Too massive to burn up naturally, it's now a ticking time bomb in crowded low Earth orbit. ESA estimates there's a 1 in 10 chance it could collide with another object within the next century, potentially triggering a debris cascade. Yet no law forces ESA to remove it, and the $100 million cleanup cost makes proactive measures politically unpalatable. This paralysis isn't unique to Europe. NASA faces identical dilemmas with its defunct spacecraft. The result, a growing collection of orbital landmines that nobody wants to disarm. Emerging solutions only highlight how fractured the system remains. Startups like Astroscale are testing debris removal technologies, but without binding international agreements, their efforts resemble bailing out the ocean with a teaspoon. The United Nations Long-Term Sustainability Guidelines, adopted in 2019, are toothless recommendations, not mandates. Meanwhile, the very nations preaching orbital stewardship continue launching satellites with inadequate end-of-life plans. Russia's 2021 anti-satellite test, which deliberately created thousands of debris fragments, proved how easily rhetoric crumbles before strategic interests. At its core, the ethics of space junk revolve around a simple but radical idea. Orbit isn't a resource to exploit, but an ecosystem to preserve. Just as we've learned too slowly to protect oceans and atmospheres, we must now grapple with the fragility of the orbital environment. The alternative is a future where access to space and all the science, commerce, and connectivity it enables becomes collateral damage in our collective negligence. Cosmos 954 was a warning shot. The next radioactive satellite might not land in an uninhabited forest, and by then, the question won't be about compensation, it'll be about survival. High above the Earth, nearly 22,000 miles out, there's a place where satellites go to die, not with fire or fanfare, but with a slow, silent drift into oblivion. These graveyard orbits are the final resting places for thousands of retired spacecraft, each one a ghost of human ingenuity. Picture a cosmic junkyard stretching across the sky, filled with the husks of weather satellites that once predicted storms, communications relays that beamed TV signals across continents, and navigation beacons that guided ships through fog. They served us faithfully for years, even decades, until their fuel ran out or their circuits failed. Now they circle endlessly in the darkness, their solar panels bleached by radiation, their antennas frozen in useless poses. What makes these graveyards so unsettling isn't just the scale, it's the paradox they represent. We push these machines to the edge of human capability, packing them with cutting-edge technology, only to abandon them like forgotten toys. Take the case of Intelsat 601, a communications satellite launched in 1991. After 18 years of service, it was nudged into a graveyard orbit in 2009, its thrusters firing one last time to clear the way for its replacement. Today, it drifts among hundreds of others, a 2-ton monument to obsolescence. The engineers who built it knew this would happen. Graveyard orbits are standard practice to avoid cluttering active orbital paths. But that doesn't make the sight any less haunting. The rules of orbital mechanics turn these graveyards into a morbid necessity. At geostationary orbit, where satellites match Earth's rotation to stay fixed over one spot, even a dead machine can remain for centuries. Without intervention, defunct satellites become drifting hazards, threatening collisions that could spawn deadly debris clouds. So operators reserve the last drops of fuel to boost them a few hundred miles higher into a purgatory where they'll linger long after their creators are gone. The math is coldly practical. It takes less fuel to dump a satellite in a graveyard than to bring it back to burn up in the atmosphere. But the consequence is a growing ring of skeletons around our planet, each one a testament to the trade-offs we make in the name of progress. Yet some satellites refuse to stay dead. In 2015, astronomers tracking space junk made a bizarre discovery. A U.S. communications satellite named LS-1, abandoned in 1977, was still transmitting. Its batteries had decayed decades earlier, but its solar panels, battered yet functional, were somehow powering a lonely signal, a ghostly beacon in the void. For engineers, it was equal parts inspiring and unnerving. These machines we dismiss as dead often cling to flickers of life, their components enduring far beyond design specs. It's a humbling reminder that in space, even our endings are imperfect. The graveyard orbit isn't just a technical solution, it's a mirror. In these silent rings, we see the shadow of our own disposable culture. We build marvels, use them, then cast them aside when something newer arrives. But unlike earthly trash, space junk doesn't decompose. It accumulates, a slow-motion avalanche of our own making. With over 5,000 satellites currently operational and tens of thousands more planned for launch in the coming decade, the graveyards will only grow denser. And someday, far in the future, when our species is gone and Earth's surface has erased most traces of us, these orbiting relics may remain, the last monuments to a civilization that reached for the stars, then left its skeletons hanging in the sky. On February 28, 2019, engineers at the European Space Agency faced every satellite operator's worst nightmare. Their Aeolus wind mapping satellite, a critical tool for global weather forecasting, was on a collision course with SpaceX's Starlink 44. The two machines were hurtling toward each other at over 32,000 miles per hour, with a projected missed distance of just 190 feet. In orbital terms, that's a hair's breadth. With only half an orbit's notice, ESA fired Aeolus thrusters in a desperate avoidance maneuver, nudging it to safety with less than 20 minutes to spare. What made this event so chilling wasn't the near miss itself. It was the revelation that SpaceX hadn't initially planned to move their satellite, believing the risk acceptable. Only after ESA's urgent appeals did they adjust course. For the space community, it was a wake-up call written in fire. Our orbital traffic system isn't just fragile, it's running on blind trust and last-minute luck. These near misses unfold with terrifying frequency, often escaping public notice until after the danger has passed. In 2021, China's defunct Hi-102 satellite shattered unexpectedly, scattering debris directly into the path of SpaceX's Starlink 1095. The collision probability spiked to over 10% orders of magnitude higher than the usual 1 in 10,000 threshold for evasive action. Yet with debris too small to track reliably, operators could only watch and wait. Miraculously, the satellites slipped past each other, but the incident exposed a gaping flaw in our orbital awareness. We're playing a high-stakes game where some bullets are too small to see coming. The math behind these close calls reveals how thin our safety margins really are. Current tracking systems monitor roughly 30,000 objects, but estimates suggest there are over 100 million untraceable fragments between 1 millimeter and 10 centimeters in size, each capable of mission-killing damage. Even a 1 centimeter bolt impacts with the force of a hand grenade at orbital velocities. When NASA timed spacecraft and Russia's Cosmos 2221 passed within 60 feet in 2024, an event with a collision probability initially calculated at 3%, it wasn't just two satellites at risk. A collision at their altitude could have spawned a debris field threatening the International Space Station and countless other assets in low Earth orbit. What transforms these incidents from technical footnotes into existential warnings is the domino effect they represent. Every near miss that doesn't happen today could become an unavoidable collision tomorrow as orbital congestion worsens. The infamous 2009 Iridium Cosmos crash occurred despite a calculated 1 in a million collision risk, proof that unlikely events become inevitable given enough time and traffic. Modern satellites now carry automated collision avoidance systems, but these are stopgaps, not solutions. Like drivers relying on airbags instead of seatbelts, we're engineering our way out of problems we should be preventing. The most unsettling near misses are the ones we never see coming. In 2022, an unknown object, likely a fragment from a decades-old Russian rocket, passed within 47 feet of China's Tsinghua science satellite. With no active tracking data on the debris, the close approach was only detected afterward through radar analysis. These stealth threats reveal the limitations of our planetary defense network. We've built a neighborhood watch for orbit, but half the suspects are invisible. Yet within this chaos lies an unexpected hope. Each near miss forges new protocols. After the Aeolus incident, SpaceX upgraded its conjunction assessment processes. The 2021 Yun high debris scare spurred improved data sharing between U.S. and Chinese space agencies, despite geopolitical tensions. Even the timed Cosmos event accelerated testing of AI-powered collision prediction systems. These incremental advances hint at a future where orbital safety isn't left to chance, where automated traffic management systems might one day orchestrate satellite movements as seamlessly as air traffic controllers guide planes. But until that day comes, every sigh of relief after a near miss carries the same unspoken question: how long until our luck runs out? The next generation of satellites won't just be smarter, they'll need to be nearly indestructible. Engineers are now weaving miracles into their blueprints, self-healing materials that seal micrometeoroid punctures like cosmic scabs, artificial intelligence that predicts failures before they happen, even modular designs where damaged components can be swapped out by robotic repair drones. Imagine a satellite that senses an incoming solar storm and reconfigures its systems in real time, or one that uses AI to dodge debris too small for ground radars to spot. These aren't sci-fi fantasies, they're prototypes in clean rooms from California to Tokyo, born from decades of watching our best machines fall to problems we never saw coming. But innovation races against an ever-darkening sky. While we're building tougher satellites, we're also filling orbit with more hazards than ever. The same solar storms that fry electronics can warp Earth's atmosphere, increasing drag on satellites unpredictably. Space debris doesn't just pose collision risks, it creates navigation chaos, forcing satellites to waste precious fuel on endless dodges. Even AI has its Achilles heel. The more autonomous satellites become, the more creative their potential failures. In 2022, a European Earth observation satellite's AI misdiagnosed a routine software update as a cyber attack, triggering a needless lockdown that took weeks to undo. The irony stings: the very systems meant to prevent disasters can sometimes cause them. the most promising breakthroughs might lie in humility rather than brute strength. Modular satellites like NASA's upcoming Awesome 1 mission accept that failure is inevitable, so they're designed like orbital Lego sets with replaceable parts serviced by robotic arms. Meanwhile, material scientists are stealing tricks from nature: titanium alloys inspired by abalone shells, fractal circuit boards that keep working even when cracked, even living coatings laced with bacteria that regenerate under radiation. These aren't just engineering feats, they're philosophical shifts, acknowledging that survival in space means bending rather than resisting. Yet for all our ingenuity, the universe keeps dealing wild cards. In 2023, a cutting-edge Japanese climate satellite was crippled not by debris or solar flares, but by an unexpected flaw in its own thruster design, a miscalculation so subtle it slipped through years of testing. And no amount of AI can fully anticipate the chaos of crowded orbits, where one nation's anti-satellite test could spawn debris threatening every satellite in low Earth orbit. The bitter truth: we're not just fighting physics anymore, we're fighting our own exponential ambition. The satellites of tomorrow will need to be more than resilient, they'll need to be wise. That might mean trading raw performance for redundancy, or accepting shorter lifespans in exchange for cleaner deorbiting. It will certainly require something harder than any alloy: international cooperation. Because the ultimate test isn't whether we can build tougher machines, it's whether we can outgrow the mindset that filled their home with shrapnel in the first place. The void doesn't care how advanced our satellites are, but it will teach us again and again that survival up there begins with responsibility down here. We barely notice them, yet satellites orchestrate the rhythm of modern life with quiet precision. Your morning coffee depends on them. Farmers use GPS-guided tractors to plant the beans. Shipping containers full of roasted blends navigate oceans by satellite, and the digital payment at the cafe syncs with atomic clocks in orbit. But in January 2016, the illusion of seamless reliability shattered. A tiny timing error in the U.S. GPS network, just 13 microseconds out of sync, rippled across continents like a stone tossed into a pond. Cell towers faltered, police radios crackled into silence, and emergency broadcasts failed across North America. The outage lasted only 12 hours, but it exposed a terrifying truth: we've wired our civilization to a system we don't fully control. The GPS glitch wasn't even a satellite failure, just a routine software update gone slightly awry. Yet it revealed how deeply orbital tech has infiltrated society's hidden plumbing. Financial markets timestamp trades using GPS clocks. Stock exchanges could freeze if those signals vanish. Electricity grids synchronize across continents via satellite pulses. A disruption might trigger cascading blackouts. Even your phone's weather app pulls data from orbiting sensors that monitor storms too distant for ground radars to see. We've outsourced our infrastructure to the sky without a backup plan, like building a house on stilts and forgetting how to construct stairs. Agriculture illustrates this dependence in sobering detail. Modern farms are essentially satellite-operated factories. GPS-steered planters space seeds within centimeters for maximum yield. Drones monitor crop health using satellite-fed weather models. When South Korea's GPS signals were jammed by North Korea in 2016, fishing boats drifted helplessly and tractors froze mid-field. The economic loss topped $250 million, not from bombs or blockades, but from missing orbital whispers. The scariest part: no one truly knows how to untangle this web. Alternatives exist, but none with satellites' global reach. Ground-based navigation systems like eLORAN were dismantled as GPS made them obsolete. Fiber optic networks can't replace satellite internet in remote regions. And while astronomers propose resurrecting celestial navigation as a backup, few sailors today remember how to read the stars. We've traded resilience for convenience, and the bill might come due suddenly. Perhaps the greatest irony is that satellites themselves are fragile. Solar flares, debris strikes, even bureaucratic budget cuts can silence them. Yet we keep weaving their signals deeper into daily life, from synchronizing traffic lights to tracking endangered species. The GPS glitch was a warning shot across humanity's bow. Next time, the failure might last longer, or worse, happen during a hurricane, a war, or a financial crisis. The question isn't whether we're dependent on satellites, it's whether we're brave enough to admit how much we've gambled on machines we barely understand, floating in a void we can't protect. Satellite failures are more than technical hiccups, they're cosmic lessons in humility. Each breakdown is a whisper from the universe, reminding us that for all our equations and engineering, space remains a realm of chaos and unpredictability. Consider the Hubble Space Telescope's flawed mirror, a mistake measured in microns yet powerful enough to blur our view of the cosmos. Or the Mars Climate Orbiter, lost because one team used metric units and another used imperial. These aren't just errors, they're stark reminders that human ingenuity, no matter how brilliant, still stumbles in the face of the unknown. What's remarkable isn't that we fail, but how we respond. Every satellite that goes dark becomes a classroom. The engineers who rebuilt Hubble didn't just fix a mirror, they reinvented how we correct mistakes in orbit. The teams behind Mars missions didn't abandon exploration after the orbiter disaster. They redesigned protocols to ensure such a mix-up could never happen again. These stories reveal a paradox. Our greatest leaps forward often come from our most spectacular stumbles. It's as if space itself demands that we earn every inch of progress through trial, error, and sheer stubbornness. The next time your GPS glitches or your weather app falters, pause for a moment. That minor inconvenience is a tiny echo of the vast, fragile web we've woven above us. Satellites aren't just tools, they're mirrors reflecting our ambition and our limitations. They show us that exploration isn't a straight line of triumphs, but a winding path littered with broken circuits, misaligned thrusters, and silent radios. Yet with every failure, we piece together a little more understanding, pushing the boundaries of what's possible. This dance between failure and progress isn't unique to space. It's the story of human curiosity itself, of daring to reach beyond what we know, even when the universe pushes back. The satellites orbiting Earth, both the living and the dead, are testaments to that relentless spirit. They remind us that the cosmos doesn't owe us clarity. We have to fight for it, one corrected orbit, one salvaged mission, one lesson at a time. So as we look to the stars, let's carry these lessons forward. Not just in the satellites we build, but in how we approach the unknown with equal parts boldness and humility. Because the greatest discoveries often begin with a failure, a glitch, or a silent machine drifting in the dark. And if history is any guide, that's exactly when the real breakthroughs